Good morning everyone and welcome back to our channel. Here we are once again in front of our very own Siemens shop turn simulator. Indeed, today we're doing an exercise of pure turning, where we will see the product you see on our right coming from a raw material and we will work on it in the first phase, which is the area on the right, and in the second phase, the entire inner hole. So first of all, of course, let's create our program file in the Program Manager. It takes us to the directory of our parts. Let us simply highlight the main parts directory. And let us create a new directory. We will call it bushing. Shaped to give it the OK. He will, as always, ask us, look, let's create another program. We'll do it in shop turn. And here, let's already indicate phase 1, since we will have 2 machining phases. And here we go. Let's already indicate phase 1, since we will have 2 machining phases. We give it the OK. And he, as always, he asks us, which is perfect, and it takes us to define our raw piece. Here, pay attention, this shaped bushing, as you can see from the drawing, is made from a rough casting, from a stamped piece. Okay, the first definition of the raw material should not be that of a stamped piece, but it should be of a cylindrical raw material, rather than a tube, a parallel piped or a polygon, with the maximum dimensions for machining, so length and outer diameter. G54. ZV is our zero plane raw piece, the type of the starting raw material of the starting raw material. So a cylinder, a tube, a parallelly piped. XA is the maximum outer diameter of our raw material. In this case, we see it here. 1 ZA. The excess material on the first face of the piece. Z is the maximum outer diameter of our raw material. What's the length of the raw material in which in this case 120, always followed by a sign minus. In this case ZB, which right now you see is telling you that something is off. I can't make a piece that's 120 long and have it stick out less than 380. So Siemens always gives you information on what works and what doesn't. How much will this piece stick out? We said that the first phase is the one on the right, so we will have it stick out 18. Be careful. Here we are doing both internal and external machining, so the temptation would be to set it to expanded. You see, actually, if we position ourselves on X3, release plan X3, possible increment, should we do it? Only for the piece raw tube. So, since we are the ones who are going to make it this hole, which is not a tube, we call it simple. For now, okay? All the other things more or less usually remain unchanged. Maximum spindle speed main. Here we go. This is a little low. We'll set it to 3500. And we will give it a sense of consistent machining. We accept if there will be problems on this thing, we will see it. After, the first thing to do is always to give it a little chamfer. Is always give a little chamfer anyway to our piece. Okay? To our piece. Okay. A chamfer is also something you do for safety. Even if maybe the raw material tells me there's excess metal 0. We always do one piece at a time. The piece. So that if arrivals, a piece that is poorly stamped or has some protrusions, we can say that they might cause problems in the following machining. A chamfer will ensure that all the machining has a starting point. Fixed, which will be the Z0 of the first chamfer. It could also be Z01. Let's go with the little arrow from this menu in, a straight circle. First of all, we need to tell it, well, I want to work with a suitable tool now. To the chamfer, so tool, I select the tool, and I'm going to choose one of the tools I have in the machine, or one that I'm going to create. In this case, I can easily use an external tool with a radius of 0.8 and tell it, look, I'm going to have you work not in revolutions per minute, but as a lathe operator in cutting speed, radius 0.8. And tell it, look, I'm going to have you work not in revolutions per minute, but I'm a lathe operator, so in cutting speed, constant 80 meters per minute in the turning plane. And I accept. This is our equivalent, which is commonly known and referred to as TO101M6 or TO101M6. Depending on the machine you're working on, M6 often rotates the turret. This, translated into ISO, would be this line. Now I want to make a straight line. The first line is an approach line, so we have a raw piece of 75 millimeters. We safely approach 80 minutes to our facing Z. How do we approach? We approach quickly. Here it is. We accept. After that, we do a facing, so still a straight line. The IX minus 2 times the tool radius, we said it's 0.8, so minus 1.6 meter to avoid the famous facing chamfer. Here I don't use rapid, but I set F0.3 to avoid the famous facing chamfer. Here I don't use rapid, but I set F0.3. We accept, and I do a facing. If this happens to you, I'm telling you this simply for the sake of record, that when you arrive at the center, the insert breaks. It's due to the fact that you have the tool either slightly low or more likely slightly high. So, it will put pressure on the facing chamfer. Maybe for this discussion, I'll make a video with a 3D. So what do you need to do? The ideal would be to put the machine into geometry, if you can't put the machine into geometry. You divide this line into 2 lines, one that goes to X20 at F03, and one that goes to X1.6 at F01, so that a very low F will ensure that in the end, when the tool starts to work poorly, the chamfer will break off. It's not a good piece of advice to give, but in workshops it often happens. Haste leads to doing this and not restoring the machine geometries. All right, let's move away for safety. Line X120. Z30. Quick. We accept. A little simulation and let's see what happens. 3D view, and you'll see something that you won't like much. You see the tool is starting to work. I checked the program, it was a bit too fast. The tool, it starts working from here. Why? Because I defined a rough stock of 105. Actually, the rough stock 75, I lean on 80 and go down. This shouldn't be a problem for you because you know that the graphics right now are quote-unquote misleading. Let's go back to editing. And we continue with our little project. So, before we go on to define the rough cut, I would like to start with a drilling. So, I go to the drilling soft key, and I perform a center drilling. So, we will work from the lathe. All right. First of all, let's look for a suitable tool. I want to drill with a 32mm bit. Let's see if we have it. If we don't have it, we'll put it in. All right, drill. 5, look. We have the bit. We have the diameter. 5. We're just going to modify the diameter. Of course, this will correspond to going to the machine's turret. Check that there is a 32mm bit in position 10. It probably won't be there. You need to put it in and zero it out. Unfortunately, with a PC, I can't show you the whole operation, but we'll have your workshop heads do some of it too. So, selection, tool, we said 32, so let's also modify the label. But we'll also have your workshop heads do something. So, selection, tool, we said 32. So let's also modify the label of the bit. Okay, 32 a million a bit. Of the bit. Okay, 32 million a bit. So it's a bit, a 32 millimeter bit. We can make it work at 1 millimeter, at 1/10 of a turn, but also 1/10 and 3, even 1/10 and 5. It then depends on the bit you use and its performance. And also from the metal. Let's say that on a C40, a 32 millimeter insert bit from Corma has done it for you. Still working at 0.13. For 150 meters is fine. Chip breakage. Okay, you see here it forces me to set a break. Chips, we will go to trick him because the insert bits don't cause breakage. Chips the insert bits. Drill all the way through. So we leave 0 at 0, 0, 1. We're going to drill up to 57 meter, so minus 57. And OD. That's when we're going to break the chip at 57. Perfect. We will have done a complete drilling. Complete drilling. And here we're going to talk about removal, chips. So, not, it won't give me any other kind. We accept the request and simulate. Let's see what happens. And you see that we have our drill bit. So, our drill bit, but you see that it created a little problem. It came out in an unusual way. I don't like it, but I also want to explain to you why this happened. The reason this happened is quite simple. Let's see if I can explain it to you. To explain it to you, we need to go into program control in single block mode and rerun our machining. You see, the tool is coming in. It breaks away, moves away, and rotates the turret. Our turret has the plate of the turret here. All right? I execute the rotation of the turret. What happens? What happens is that our plate is here, but I have mounted a drill bit that is long. Sunt pas misimita. The drill bit, of course, extends beyond its own length, compared to where the turning tool is located. At that point, when it goes to work, it collides. How do I solve this problem? Here is the force. You see that it collided here. This is the force of a graph. So pushed. In reality, you know that the piece isn't here, but you can't work with such tight safety parameters. So pushed. In reality, you know that the piece isn't here, but you can't work with such tight safety parameters. You go into Edit. You go into Program Header, and you tell it Point Change Tool ZT. I want it to be at least 250 because I have a drill bit on. Let's accept it. Let's simulate. And let's see what happens. Let's go into Program Control, remove the single block, and start. You see that the problem is no longer there, and that the drill bit has moved away in a more correct manner. Perfect. Let's go back. In Edit, we have drilled. Perfect. Let's define what the profile of the raw material is regarding our machining part. I mean, this. So, the profile of the raw material. Let's define it. As a new profile, I had already shown it to you in the other video. Let's put in the name and call it Indeed, it is indeed simply just blank. Okay, we accept. Starts from Exio. Zeta, which is this point, and we're going to define a size for the blank. So we go up to x75. We accept. We go to z43. And we tell it that we're about to finish with a radius that isn't specified here. We'll specify it ourselves. Radius 10, 5, because otherwise it's a diameter of radius 5. We accept, and we go inclined from 105 alpha to 105 alpha, inclined at approximately 60, so 90, 120 degrees each. And here we also have a radius of 5 mm. We accept here. We are, and let's go. In less than 60, we make it 80, so Z80. We accept. Here we are. Maybe minus 80 was a bit too much. But basically, we need to work up to here. So that works for us. Perfect. And let's go back. So, here, to close the profile. Here we are, we've closed the profile. Here's our right blank part. We accept. And we've created our profile perfect. Now what we need to do is the turning of this profile, excluding the groove, okay? Of this profile, excluding the groove, okay? We'll do the groove separately with a groove tool. A groove that has a peculiarity. On one side it's inclined, and on the other side it's straight. Again, a new profile. Let's put the name. The name, and we write it down. Finishing external. I have the habit of capitalizing the first letter. Then it looks bad. Here we are. We accept. All right, the external finishing. We've already chamfered it, so we're going to do it. Starting from the diameter of 59, which has a chamfer, so the chamfer is 1. Let's say the starting point is at x55, 55. We accept, and let's start moving upwards at x59, x15, with a chamfer of 1 mm. We accept, and we move at z5, so horizontal movement to z5. Here, we don't have any radii, we don't have anything, so we accept and make an inclined movement of 15 degrees that takes us to x70. x70. Alpha 1, and 15 degrees. So 90 degrees plus 15 makes 105. Here, I've already told you, if there's no one, no edge, no radius, if you want to be particularly cool, you can add a radius of 4, so that your client will have it in hand, of pieces that won't have any points. Let's talk about chamfering, and you can always do this. It would be nice to have it by default. We accept horizontal movement up to where you see that we don't have a dimension, but we have everything we need to derive it. So, as a minus 60 plus 5 is 65, so it's another thing. 60 plus 5 is 65. So 60 minus half of 10 is minus 55. So Z minus 55. We accept. Here we are, and we move up to x100. x100, with a chamfer of 1 for 45. x100. Chamfer 1. We accept. Perfect. And now let's do our final part. So we move horizontally and we are going to give it Z minus power money 5. We accept. I don't like to finish like this, but to finish at the diameter of the raw material. So upwards, X. 107. We come out 2 mm from the raw material. We accept and we accept. We have defined our workpiece. We don't have any specific tolerances. We don't need any special tools. We insert a roughing operation. We select the tool, the rhombic one. Can do everything for me. We give it the OK, a tenth per revolution. Now let's do something. What do we want to do? Roughing plus finishing. Here it is. So, we have this F that we position at 0.3, which is the roughing F. You see, if we position ourselves on top, it tells us feed rate, 170 meters. That can work. And the finishing F is at 0.18. Longitudinal roughing. Each roughing pass will engage the cutting edge for 1 millimeter. I would say that's too little. We are using a CNMG 12. Let's engage it for at least 4 millimeters. The cutting depth, default over metal, of the material being processed is important to consider. It tells me a tenth to work well. So is it diametrical? Or radial? It's radial. So finishing over metal in X, 0.35. To work well, a tool, especially in X, must not remove too little, otherwise it will reject. In Z, a tenth is always fine. We don't set it because we want to work continuously under squareness. We don't do that. We accept it. And let's simulate. Let's see. Simulation impossible. The raw piece is not used. Okay. What does it mean? Let's go here. Wait, because here it is. Profile. You see that here, Bill. Type of the raw material. Do you see, or do I want to use a cylinder? No, I don't want to use a cylinder because I've defined a profile, so I want to use the profile that I defined. Let's accept the simulation. You see that it no longer gives me an error. This is important when defining the raw material. Look, it ignores the raw material and goes straight to roughing. And finishing, I've already done it the same way. Tool. Ignoring the dimensions of the starting cylinder. Here we have our processing. Let's go back to edit. Let's go back here. Where we made the mistake be bleh. It's a description of the raw piece. Normally you find it in a cylinder. I'll repeat it for you and show it to you again. So that error, simulation, impossible, the raw piece is not being used. What does it mean? Here I've made two definitions, okay? So having made two definitions of the piece, the machine doesn't know whether it should rough out according to the raw piece or the finished one, because for it there are two profiles. So I go to the definition of the raw piece and I tell it, let's work according to the specified profiles. I accept, and I emphasize that the machine will ignore the cylinder in turning. That the machine will ignore the cylinder in turning. Look, here so you can see it well. See? Let's break it down again. Okay. The machine breaks down, the machine is out, and then you see it always starts from the definition of my profile. Great. Let's go back to edit and focus on this nice groove. We're going to create this nice groove from the menu, turning drain and groove. Here it is. How is our groove? Our groove, does it have flat walls? No. Our groove has walls with inclinations and radii. Let's define it. Let's select a tool. We can do it. We have a groove of 10. I would go to take it. Obviously, you take the one that is as thick as possible. Do you see that it's 3? Let's go to the tool list. And let's modify the characteristics of this insert. Then, of this insert, we will modify it in the turret to at least a 5. Besides writing it in the description, let's indicate the machine we are using. An insert of 5? We have to force ourselves to tell him, using ShopTour or ISO, we decide on tool radius compensation and table completion. In ShopTour, he decides, and we provide the correct data. In ShopTour, no, it's him who decides, and it's up to us to provide him with the correct data. Let's transfer to the program millimeters per revolution. A cut of 110F is more than enough. Let's define a couple of things. A cut of 110F is more than enough. Let's define a couple of things. So, external position, frontal, internal, pulled, external. Starting point of the programming. You see that we don't have this point, we only have this one. Okay. So, we need to tell the machine to work according to this starting point of the profile. Now, let's go. To give the coordinates of our groove, the coordinates of our groove are x70. Here we are, which is the outer diameter. So, 70 z. It's this point, minus 55. T1, the incremental or diametrical depth. Sorry, but there was a mistake here. I made an error. Box. So, minus 55. B1 is the depth at the bottom of the groove, but we don't set it. Now, let's think about it. Give me a second. Here it is, sorry. B1, 10 mm. T1, the depth, or the radius. Let's see. I don't see a dimension. The depth, or the radius, let's see. I don't see a dimension. So let's use 59. We're not going to complicate our lives by looking for dimensions. Let's say that this groove reaches a diametrical depth. So, absolutely, 59. And let's go take a look. Awena. In this case, it's 0A2. In this case, it's FS1. Radius in 0. Because it's completely sharp-edged. FS2. Radius 2. So, let's convert FS into a radius. Otherwise, it will create a bevel. FS3. There's nothing. Let's set a radius. There's nothing. Let's set a radius of 0.4 equal to the insert. FS4. There's nothing here. Let's also put a radius of 0.4. D. Let's put 0 because we're working with a planted setup. Excess material, be careful. 0.2, 0.2. All right, but the groove, we rough it out and finish it. How many are we repeating? We're repeating one, we're only doing one, we've entered all the data. Let's accept and simulate. 3D. But how easy is it to program in the shop? Perfect. Turn. We have done our external profile. Well, at this point, my advice, since we've been at this video for a while, is to pause the video, go relax, maybe take a look at what we've done, and continue later or tomorrow. I, on the other hand, will continue with the creation of the internal profile, an internal profile. Later or tomorrow, I, on the other hand, will continue with the creation of the internal profile, a profile that I find quite challenging. Why do I find it quite challenging? Because I find it quite challenging. Why? The data we have available isn't that much. It would already be complicated to draw it. But in reality, there's everything you need. It's just that it's not easy to program, it's not easy in ISO, it's not easy in conversational mode, you have to work on it a bit. I didn't prepare it on purpose because I want to make mistakes together with you. Let's see if we're good or if we get confused. So first of all, we need to determine a profile, so that's the complicated part of the job. Let's go to the end of our program, turning profile. New profile. And we write to him internal. You might think to write moved, stuff, tuba, but we write internal. We accept it and move on to define the profile. Let's start with X59. And we say to him, accept. Now go down with an angle of 90 degrees and create a beam for me. So minus 90 degrees, I would say minus 90 degrees and create a beam of 1 millimeter for me. Do you accept? All right, I'm going down. And now? So what do I do now? I'm doing a circular interpolation. What data do I have available? First of all, I have the direction of the line, which is counterclockwise, and we're good. Then I have the beam. We have it. The X. Final, not final. No, we don't have it. Let's see, the Z, we don't have it. We don't have anything at all. We have it, but the I. What is the I? The diameter of the central point, which is 24. Do we have the K? The K is -8. Selection, dialog. There's something that doesn't add up. Here it is, selection, dialog. Look here, TikTok. You see where connection, Livala, accept dialog. Perfect. We accept the matter. Actually, we don't accept it because we didn't tell them one thing, the bevel. You see, I'll finish with a connection of 40. And we accept it. Perfect. Now, we have this. It's always a circular interpolation. It's always a counterclockwise path. It's always a radius. Tarsindo. We don't have the final X. Oh yes, we have it. The final X. The final X is 35. We don't have the final Z, but we have the I, which is always 24. The K, which is -40, and those are the coordinates of the center of the radius. Here it is. Selection, dialog, what is he doing? It's not really clear. And here I'm struggling, guys. We accept the dialog like this, and let's see what else we can offer. We don't have alpha. You know, I don't think that I've put together anything good. So let's come back here. We did this. You understand that it's difficult here, because we did this. So let's go ahead and delete it. This. Let's delete the delete element. We're here, let's go back. We've set the radius to 40. So at this point, let's remove the radius. We accept. And let's go take a look. To our insert. Another radius, done according to a clockwise path. Its radius 40. According to a clockwise path. The only thing we know about it is that it's approximately radius 40. Being exactly in the middle of these two circles, we have these two circles. We have a chi, which is located at 48, 32. It's the difference between this and this. 32 is the distance between Q and A, so 16. Plus 8K is minus 24. We accept. But it should give me a dialog. Tangent to the previous one, little marker. Here it is. Select the little marker, dialog. Look at it here. Found it at. This is my radius, 40. Accept, dialog. We accept it. And we have it here, perfect. Now, we have the other linear interpolation, circular interpolation, counterclockwise travel. So, this one is right. Radius 13.2, like x. 30. The undefined, the 24. X position of the center, k minus 40, z position of the center, alpha. Select dialog. Here it is, here. Done, guys. Accept dialog. Here it is, our profile. You see, I didn't prepare it or just think it through. Together with the CNC brought me and guided Menina to the correct solution. We accept it. Perfect. Let's rough it out. In this case, I want to make my life easier. I rough it out and finish. I select the tool, a 35-degree finisher is fine, okay? Let's leave these parameters. Internal turning. An internal finisher does not take away much material, especially if it is a I'm just focusing on making the profile. Guys, under squaring, in this case, we say yes. Because you see, I'm going back in here, we accept and simulate. Impossible simulation, the profile is missing. Of the raw piece, sure. Because when I definitely and indeed certainly enter a mask, I always have to tell him. Always think that she maintains. The last one, the last setting made, So we had previously worked on a profile and now we are working on a cylinder. We accept. Let's see if the simulation proves us right, because on the work done. So let's block the release plan. For this work direction, the release plan is not defined. An error that is due to. This is information that we provided at the beginning of the program. At the beginning of the program, we planned for external machining. Now, in fact, our piece has changed from a cylinder to a tube because we have drilled and are working internally. It requires a different release. A simple release means that when we finish machining, the machine releases in height. In Z dot. In reality, we no longer have a cylinder, but we have a tube. A tube whose hole has been brought to 32 mm by our drill bit. So we assume a tube with a 30 mm hole, but the release is no longer straightforward. Okay? Or at least it is a simple release, but it's a simple release that also requires a release on the inside. Okay. Or at least it is a simple release, but a simple release that also requires a release on the inside. A release that we will bring to 5 mm. Let's hope it's enough. We accept and simulate. So let's see what happens at this stage of the simulation. Let's see if it triggers an alarm. You see that it no longer triggers an alarm. Here, however, we are struggling to see the internal machining. As a result, let's change the view. It's too fast. We're in 3D. Let's start by looking at the side view. Here it is, an additional views, partial section. Perfect. Do you see that we have our profile here? Let's go ahead and do the machining. And here we go. Do you see that the tip is just widened in this case? Sometimes you need to adjust the graphical simulation to meet our needs. You see that it does the roughing and finishing of the profile. Great. Perfect. We've completed 100% of the machining on the right side of our product. The machining of the right side of our product. We can go back to 3D. We can go back to 3D. We can also go to... Wait, still in 3D? There's a way. Point of view. Let's see. Details. Cut. Perfect. Active cut. And here we can expand our cut in all the directions we want. After a second, the machine will make the cut. You see, when you move it, the piece comes back intact, and then I'll show you the cut that was made. Let's go back. Well, having completed this first phase, let's focus on this one. Second phase. Okay? The work processes are very similar. The geometries involve change. So let's go to the Program Manager and highlight our program. With the soft key, let's manipulate it. First, let's copy it. Let's copy it and paste it in the paste. The machine tells me, of course, I can't copy a program with the same name in the same directory. Let's go to change the name. Let's open it. And here is our program. As for the starting block will always be the same, because like it or not. In this case, the starting raw material is asymmetrical. We're working on 50%, with one side already done at 50% on the other side. Now guys, I'm going to go a bit faster. Let's see if you can follow me. You will always need to insert a chamfer using the same logic as before, along with a photo and a centered hole. The only thing to discuss is the centered hole. You see, it does a Z1 down to minus 100 centimeter. Since it's 120 long, 57 times 2 doesn't make 120. Let's increase it. At minus 65, the depth, and we accept the piece. The raw material is neither more nor less the same. It actually changes the geometry of the finished product. And so now we're going to modify it. Or we could also just start from scratch. In this case, we're going to delete all the elements we've added and go to the first point. To delete all the elements we've added, and let's go to the first point. The first point will no longer be at 55. We have a diameter of 60. We've already laid it out. So let's start from a 62. We accept it. And with the soft keys, we start to move. We need to think in reverse, because we'll have the piece in the machine. In reverse, compared to the drawing, first we go up to X68, and we finish with a 1 millimeter chamfer. We accept. Let's move to the left. Dosage, -5. We accept and insert a circular interpolation. Be careful. We are reading the program in this direction, but the machine moves in the opposite direction. So, we have a clockwise rotation with a radius of 20, ending at X, where our circumference will finish. We've got 68 Z, where our circumference will end, minus 25. And I would say we don't need anything else, except for a section of dialogue that will tell us, but look how we do it, because I didn't give the I and the K. Select dialogue. Can you do it like this for me? I accept the dialogue and I accept everything. Let's ignore the discharges, because Siemens will handle those separately. And let's go to Z, minus 12. Let's lift up. X, 100, with a chamfer, from 1 millimeter. And we finally finish our profile at Z, minus 70. We accept, and we accept. We've inserted it, the groove no longer exists, so there's no real cancel. But if you, with the software, or you press cancel on the keyboard, it gets deleted, or alternatively you can cut it out. Now we have the internal profile. Great. Let's also modify the internal profile, because we're basically doing the same processing steps that we did in the first phase. Here too, let's go ahead and delete the elements. Let's start from the beginning. We have a hole of 48, so let's start from an X of 55 me. Let's accept it. Let's lower it and go to X. 48, with a chamfer of 1 for 45. Here we need to do some calculations because we don't have any. The distance quoted from here to here, but we have it in negative, as it should be relative to the starting point on the right. So we need to go to Z minus 20, 120, minus 100. So Z, minus 20. Accept the. Now we lower ourselves to X40. X. Here too we ignored that. Unload. Final. Chamfer. 1. Accept. Z, minus 30. Another 10 millimeters. Z, minus 30 or minus 10 in increments. We accept and lower ourselves to X. 30. With a radius of 1 millimeter. So we accept this, and we finish the machining at Z, minus 5. Here we accept, and you see that in no time. We have been following the same line. From the previous program, we've done all the machining that interests us. What's missing? What's missing? For what reason? Let's go to editing. Let's go to roughing undercuts. Advancement in undercut 1/10 per revolution. We accept the simulation. You see, it's easy to understand the mistakes. Just look here. I have done the roughing and finished with the same tool. Obviously, having selected a tool. This radius, it made it look terrible. Let's go to selection. Tools. Tool list. Let's create a new tool. Lathe tool. Finisher. Okay. Perfect. Let's transfer it to the program and simulate. Confirming, yes, I confirm, we accept, and simulate simulation impossible. Tool radius too small. Table issues, tools. I select tools. I hadn't set the tool radius. See how smart this Siemens is. It doesn't let you make mistakes. We accept. It doesn't allow you to make mistakes. We accept. Only with turning tools? Or am I getting everything wrong? Today I said, I'm in a hurry. Yeah, I messed up. Look here, I select tools. We accept. Here we are. It's nice to make mistakes too. When you're doing these tutorials so you can see how fallible can even someone who should theoretically be capable be. But above all, you immediately realize how easy it is to communicate with this CNC. Did we do the inside right? Here it is, partial section, the inside. We did it well. What do we have left to do? The two outlets in E. Our piece is finished. Let's go back to edit. Good. Let's go to the end of the program. Turning outlet. Perfect. Now I don't have it in front of me. The catalog, accordingly. I trust a bit in what's written in 1 for 0.4. Yes, I want to do it. I want to do it. I want to do it with my tool. Okay. We'll leave the parameters in here. XOR. Here it is. So 68. 0. Minus 55. So here you see that it's not 68, but 67.5. Perfect. The X is this depth that we will have here, which is 0.5. And for Vx, we set it to 69. If you want to clear out this whole area, you can also set it to 105. We accept. Basically, the outlets are already included in the price. Included in the price. Taper and discharge. Done. Look how nice it is. Edit. Turning. Discharge. How do we do it? We're doing it inside this time, and consequently, we'll give it 48. 47 and 5, 0. We'll give it less. We'll give it 20 NVX. 40C. Let's accept and simulate. I'll tell you the reason right away. I selected an insert for internal machining. So tool selection, finishing, internals. Okay? We accept. Simulation. You can see how it respects the raw material. It roughs and finishes. And it does. The edge. As you can see, it's done well, but it's done with little depth. So, edit. Let's go back to the edge. In fact, it's not 47.5, but it's 48 and 5. Okay, I thought from the outside and not from the inside. Let's accept and simulate. And go on. How nice it is to make mistakes. In these moments, it's nice because do you realize the communication that this CNC has with the operator? It's a very, very, very high level of communication. You can see that now the internal discharge is being done correctly. Perfect. We want a 3D. Let's take a 3D. We want to move it. Let's move. Let's see everything we need. And our piece is finished. We've completed the first and second phase. It's a long video. I hope you watched it in multiple stages. I hope I managed to capture your attention. I apologize. And sometimes I too stumble upon some small mistake, but it's part of the game, especially if you're working in a company where you might have 7, 8, 10, or even 20 lathes, one with a sim and none with a fan, with a mix of 9. Learning everything by heart is not only nearly impossible, but it's also counterproductive. You need to learn to communicate with your machines. Remember that they tell you everything you need to know. Some, like sim, are more intuitive, while others are less so, but in one way or another. Whoever designed these CNC machines made sure that the operator can communicate with them, with these machines, and that these machines can communicate with the operator. Well, I hope that I have been helpful to you with this video, and if so, I hope you are. So, make sure to subscribe to my channel and share these videos with everyone who has a passion for mechanical processing. Thank you for your attention, and until next time.